People give you credit where you don't necessarily deserve it. Notice I just put exponential functions. The actual title is exponential functions in their graphs, but I don't plan on doing much in terms of their graphs today. What I really want you to understand is what exponential functions are and how they grow rapidly, right? When you think about exponents, a lot of you guys will think of like squared, something squared or cubed, right? Um, let's talk about the definition of exponential functions. It says the exponential, I'll give you the formal one and then the informal one. The exponential function f with a base of a. I'm just going to put the a like so that you see that it's a letter, not a word. Is denoted by f of x equals a to the x power. When we're talking about exponential functions, what it means is our variable is in the exponent. It's in the power, right? Notice our x is up here. This could be written as like f of x equals 3 to the x power, right? A is just some input for a number that we haven't determined yet, right? What we're saying is our unknown, the thing that we're trying to find is our power. It's our exponent, right? And that's what makes it an exponential function. Some things that you need to know. We're talking about where x is not equal to 0. Or 1. Can also, x is not equal, sorry, not x, a is not equal to 1. So tired today. So where x is not equal to 0, a is not equal to 1, and x is any real number. Right? It can be any number that's real. And we're not going to get too deep into this right now. Today we're going to start with just evaluating exponential functions, and then we're going to talk a little bit about the natural base, the natural exponential function, and then we're going to just do some compound interest problems, and so that you can see how kind of all that stuff works. It's a really good thing too, because you should know how like credit card companies charge you interest, right? We're not talking just about like the interest you can gain on money you put in a bank, but also how like if you buy a car or you have a credit card and how they charge you so much money for using them that sometimes you guys think you're getting a good deal, but if you put it on a credit card and you're paying interest on all that, you're not getting a very good deal at all. But we're going to start with evaluating exponential functions. When we say evaluating anything in math, exponential functions, they're basically going to give you a value to put in, and you have to come up with a result, right? So when we're evaluating exponential functions, I call anything with evaluating just calculator math, right? So if I have, say, f of x equals 2 to the x power, I want to know what it is when x equals negative 3.1, right? And let's write them all down. Let's also go be f of x equals 2 to the negative x when x equals pi. And let's see, f of x equals 0.6 to the x power when x equals 3/2. Let's see if I can. It's easy though. It's super easy. So what I want to do though is see if I can make this like half the size and bring about my Desmos graphing calculator over here. I think I can split this screen. Of course I can't right now. I don't have that extension anymore because I switched over to Chrome and Chrome ruined everything. So you're just going to have to bear with me on this one. Our first one that we have, if you look at it, we did f of x equals 2 to the x power. And we want to know what happens when we plug in negative 3.1 into that power and what that's going to equal. And all we have to do is plug those numbers into our graphing calculator, which is right there. So if I have that, I could put it in as y, or I could put it in as f of x, and I could go y equals 2, raise it up, up arrow. So that little above your 6, there's a little up arrow, a little hat, and that will allow you to raise something to a power. Yeah, shift 6. And we're going to put in, so what is it? It's saying that x equals negative 3.1. So we're going to put in negative 3.1 up here. And you're getting your result right here. We don't care so much about the graph of that. We just want the solution. And if we look at our solution right here, we've got 0.11669291. And you're going to reduce that to however many. It'll usually tell you, like in your homework, it'll say reduce to a certain number of decimal points. Go to like the fourth one? Yeah, for us, let's say we're going to go to the fourth, because what we got was 0.11669291, and you saw that it went on. So we're going to just send it to the fourth decimal place, 1166. So it's super easy. These are super easy when it tells you to evaluate. If we look at this one, we have f of x equals 2 to the negative x power, and then we're going to plug in pi. So when we change this is just 2 to the negative x power, and what are we putting in? We're putting in pi, right? But it's negative x, so I'm just going to put it in as, hopefully they have symbols here I can use. No. You need something after the minus symbol. I know that. I was hoping that, there we go. So that little plus there, it looks like, no, that won't do it. Settings. How do you do pi on this thing? On a regular calculator, it's pretty easy. Wonder if I could do Desmos Scientific. Let's see if we can get that going. My video is going to be so good. It's just me finding stuff. There we go. So in this one, I could go 2 raised up. We could use the same thing, shift 6 to raise it up. And now we're talking about it's to the negative x power. So we need this negative, and then we're going to plug in pi. And then we've got our answer right there, 0.1133147. So it's really easy. You guys kind of get that, right? This is, you're just plugging things in. Once you know how to put in that power, things you want to remember is if you have a negative power, make sure that if you're putting in something negative as well, if you're like say I had, this was to the negative x, and what I had to enter was like -3, that you would do it like negative, oops, gotta raise it up again. You would want to go negative parentheses, then -3, so that you understand that what you have to do is to not lose one of the negatives while you're going. Does that make some sense? So if this was 2 to the negative x power, you want the negative from the negative x, and if you're inputting -3, you want that negative as well, which is a nice even number for us. Do you guys follow that? Did that make sense, or was it ugly? The next thing we want to talk about is the natural base E. And today we're just introducing a little bit the natural base of E. And then we'll move into more of how it works as we get into logarithms and exponents. The natural base actually negates a logarithm. So once we learn it, it allows us to solve for those unknown x values as we move on. But for right now, we just need to know that the natural base E is just a lowercase e. It's symbolized by a lowercase e, and it's equal to 2.718 blah 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 forever and ever. It's kind of like pi, it goes on forever. But its general position, like pi is 3.14, the natural base e is about 2.718. I can't remember all the other numbers. And we call this we use it in terms of if we have f of x equals e to the x power, this is called the natural base function. The natural exponential. I wrote the natural base up above. The natural exponential function, right? On your calculator, you'll always see it. It always shows up on any calculator that you use. Here's our scientific calculator. If we move into functions, we should see a lowercase italics e down here, right? You'll see it on any calculator that you use. There'll be that lowercase e. That is just that natural exponential function. A lot of times it's going to share a key, like on a regular scientific calculator, with ln, right? And it is because they are opposites, right? So E and ln negate each other. E is the natural exponential function. Ln is the natural logarithmic function. And they are opposites of each other. They are inverses. So you'll see them together a lot. And it's why we're learning it right now, but we're kind of introducing it today because it works for us in terms of compound interest, which is one of the things we're getting ready to move into. When we're doing evaluation of natural exponential functions, evaluating, it works just like doing the regular exponential functions, only what you're always raising up is e to a power. Exponential functions. So if I have, say, f of x equals e to the x power, and we say that x equals -2, we would just go to our calculator, right? Doesn't want to stay up there. And I would put in e. Usually with an e, you'll get automatically, even better. You don't even have to put in. See right here where it says e to the x? It raises it up for you. And then you're just going to put in whatever your x value is. So if my x value is -2, I'm just going to plug that in. And it's going to, look, it's already given me my solution of 0.135335. And you're just going to round it to whatever. Usually it's about 4 digits. It'll ask you to round it to. So we would go 1353, right? 0.1353. If I was asking you to raise it up to the 0.25, right? We just go back a little bit. We'd raise it up to the 0.25 power, right? And you get your solution. This is really easy math if you know how to plug it into the calculator, right? So you're going to want to go to the function tab if you're using Desmos, right? And you're going to go, you can click E, but then you have to raise it up yourself. But we already have an E to the X right here. So you might as well just use that. And then you can just fill in whatever X is. So super easy stuff up to this point, right? And this is this is like 8 of your 10 problems is just plugging numbers in on a calculator, right? It's either doing it for the natural base e, or it's doing it for the exponential function when you're plugging in for the f of x, right? And that's it. That's primarily most of what you're doing. Everything else is using this knowledge to find what we call compound interest. Now, compound interest is interest that is usually either charged to you or charged from you. If that makes sense. Like if you put money away in, say, an IRA account and you got a percentage on that money, it would be regularly compounded. The interest is accrued a certain number of times per year over a length of time, right? And then that money builds because if you leave that interest in, the next time it's accrued, it's also being accrued to the interest you've earned. And it's how rich people stay rich. Like if I could put $1 million into a bank and not touch that money, and it got interest compounded regularly, well, say I got 10% interest compounded, right? It's never going to happen. But that's like another $100,000. 10% of $1 million is 100,000, right? Or 10,000, something like that, right? Well, the next time my interest is accrued, it's on that money that I made in the interest before, too. So my money is constantly making money. It is why I tell students or my own kids that once you start making money, put away a couple thousand a year. Open up an IRA, put away money every year, pretend it doesn't exist. And I swear to you, in 25 years, you'll all be millionaires. You'll all have at least $1 million in the bank. If you can do that every year for the next 25 years, by the time you go to take that money out of the IRA is usually a really good one, like a Roth IRA, but it's an interest bearing account, you guys will have made at least $1 million, right? But people don't understand it, or we need our money. Like I can't afford to put away $2,000. It's well, stocks can be dangerous, but IRAs, what they do is they spread them out over different stocks. They pool everybody's money, and then they invest them in different stocks, right? So it's like a mutual fund almost, but it's fairly safe. So we're going to talk about compound interest, or how rich people stay rich, and how I wish I was one of them. Compound interest is pretty easy to figure out if you know interest. It's pretty easy to figure out if you know the formulas. There are two formulas for compound interest. The first one, formula number one, is for n times per year, which means some disclosed number of times per year that interest is being compounded. N times per year. So if it's quarterly, that's 4 times per year. If it's bi-monthly, that's 6 times per year. If it's annually, that's 1 time per year, right? Over a certain number of years. But for n times per year, you're going to use the formula A equals P. I'm going to tell you what all those things mean. Times 1 plus R over N, which is rate over number of times per year, raised to the power of number of times per year times the time it's kept there. And I'll list all those things on the side here in a second. I'm just going to put the other formula. The other one is for continuous interest, right? And it'll always tell you if it's continuous. Continuous. I feel like I spelled that wrong. I think there's another U in continuous. I'm tired today. I'm not used to this teaching anymore. I had a week off. I forgot how to do my job. Continuous. Did it again. Interest. Continuous interest I always call PERT, because it's P E to the RT, and I always think of it as PERT. What do all these letters mean? Well, the P is the principal. It's what you're investing, right? What is that initial amount you put in? Principal amount. N is number of times per year compounded. Compounded annually, right? T is the amount of time you leave it in years. So if it's 6 months, it's 0.5 years, right? If it's 25 years, it's 25 years. It's 25. R equals rate. That is the percentage in decimals, right? Percent in decimals that you are making on it, or they are taking from you on it. Right? So if they say 3% interest, that is the rate, right? But you want it in decimals. So if they said 3% interest in decimals, that would translate to moving the decimal from here to here. And so it would be 0.03 is what you would put in, right? Did I miss anything on this one? No. Down here, everything is the same except for we have that E. What is E? It's that 2.71. You don't need to put all the numbers in, right? You just need to do E and raise it to a power. So these are our only two formulas that we deal with when we're dealing with compound interest. So if I say can find the problem that I wrote down. I gotta hurry because we only have like so much time left. So we want to find the interest, right, on a $12,000 principal. $12,000 principal that we're investing, right? Find the interest on $12,000 investment. Right? At an annual rate of 3%. Do I want more than 3%? Heck yeah, I do. Let's see, an annual, I'm getting messy here. Over a period of 5 years. When it is compounded A, quarterly. How many is quarterly?
4.
Yeah, 4 times per year, right? B, monthly, so 12 times per year, right? And C, continuous. Continuous. Look, I keep forgetting that second U. So quarterly, when we look at it, we're going to use for anything other than continuous, we are going to use this first problem, right? Everything else, when it's continuous, we're going to use PERT. So if we look at this quarterly, what we know is our P is our principal. That's $12,000, right? We're told that our rate is 3%, so our R equals 0.03. Our time, our T, well, it said 5 years, so our T is just 5. What else are we missing? Our N, how often is it compounded? Well, it is compounded quarterly, right? So N equals 4 because quarters are 4. And now all we have to do is plug those numbers into the equation, right? Our A, that amount that we're going to have at the end of it, is going to be equal to our, let me rewrite the equation down here. A equals P times 1 plus, what is it, N over T or R over T? N over R, R over N. R over N. R over N raised to the NT power, right? So our principal we know is 12,000, right? Times 1 plus our rate, which is 0.03, over N, which is 4, times N times T. So 5 times 4, right? What is 5 times 4? To the 20th power, right? NT. And so all you have to do is plug this into a calculator. I like to do it in pieces a little bit, but it's literally all we have to do is just plug this into a calculator. So let me see if I can.
Wait, so how did you get to 20?
I multiplied my T times my N. See how it says raised to the NT power?
Okay.
So I took 4 times 5, and that gave me 20. And now we just need to plug it in, right? So and so that's what we're going to do. All we have to do is we've got 12,000 parentheses 1 plus, we've got 0.03 divided by 4, right? So we can close out that parenthesis. And then we can just raise it up, shift up arrow 20. That's all there is to it, right? It actually gave us right there our solution, right? We invested $12,000 at 3% compounded quarterly over the course of 5 years, and we came out with $13,934.20. What does that mean? If we look at it, it means we made almost $2,000, right? We made $1,934.21, just leaving that money there over the course of 5 years.
5 years, year, $2,000.
Yeah. But just by not doing anything, just by leaving it there. Now, if you put in more money, you're going to make more money, right? Which is why I said it's how rich people stay rich. Because think about how much money they can put in to earn their money. But think about this: the next time that it's compounded, you aren't doing it on $12,000. You're doing it on $13,934. Right. Yeah, and if you keep putting more money into that account, it gets bigger and bigger and bigger. That's why I said if you add money every year, $2,000 every year, you're going to be a millionaire by the time you're ready to take that money out. The trick is you got to be able to leave the money.
Dude, I earn $12,000 a year.
Well, you'll make more eventually.
I know. I was thinking, I was like, dude.
So this is quarterly. This is what we make quarterly. It says we also want to do that monthly. What changes when we do it monthly is the number of times it's compounded, right? When we compound monthly, that makes that 12. And now we're doing 12 times 5, which is 60, right? And we have a new amount, right? It's really not that much different compounding it more. It's what, like an extra $5? What about continuous, though? Now, continuous, if we go back, we can see that continuous, we don't use this same formula, right? We have to use the A equals PERT, PERT, right? Our amount equals P e to the RT, right? So when we're looking at that, our principal is 12,000. And then we've got E. And we'll put that in as E. And our rate times time. So for us, that's going to be 0.03 times 5. Does that make some sense? Because really,
things in and putting into
it really is. It's just knowing how to plug it into the calculator. It's knowing the formula and how to plug it into the calculator. This isn't math you're going to be able to do in your head, right? You have to use a calculator when you're doing it. So let's look at that PERT problem, right? We're saying that we have 12,000 as our principal. Then we have E. We'll do E raised. And for what we're raising it to, I'm going to put it in parentheses. I'm going to go 0.03, close parentheses, and then open another parentheses and multiply that sucker times 5. Right? And here we have 13,942. So you'll notice that continuously, it doesn't make you a ton more money, but it does make you like $3 more. Right? But think about this with huge amounts of money. So does that make sense on how to fill these out? Because this is literally as difficult as it gets, right? It's just knowing how to put these things into the calculator. So I have every confidence in your guys' ability to be able to do these assignments. Um, it's literally a couple of evaluate e to the x's and a couple of evaluate um, the 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 regular exponential function a to the x, whatever that is, and then two where you have to do compound interest for different amounts. Just remember, the only thing that's going to change in most of them, like if you're given quarterly or monthly or annually, the only thing that's changing is your n. You can just go in and change those. Um, Continuous, right? You're doing the same thing, you're just using a different formula. Yeah, I kind of like it. Like we would throw amounts out in my class, like what if I saved this much over this amount of time? Like how much money would I make? Or if I, started a savings account for my baby, like the time they were born, by the time they turned 18, if I put in this much money every month, how much money would they have at the end? And we would figure that stuff out. And I thought it was kind of cool. Um, so this is the extent of your homework. Like it's really, it's nothing difficult. I know it took me a long time to explain it all, but
I found one problem with the homework.
with the